A note, on some of my recordings, there have been some sound issues in some of the recordings. The sound is completely chopped up, and we're trying to figure out why. So at the moment, I'm running some software in the background that may or may not cause some interference with the recordings. Please be aware, today's recording may be a little iffy if you need to come back to it. So we've been looking at definite integrals, and the fundamental theorem of calculus tells me the definite integrals are found using antiderivatives. To that end, I want to change our notation for an antiderivative and relate it to an integral. So I'm going to use that same integral symbol, only with no numbers. So this is, if I put an a and a b on there, that's a definite integral. If I don't, we're going to call this an indefinite integral. And that is actually going to mean our antiderivative, and the general antiderivative at that. That's why there's a plus c on the end there. I don't know which antiderivative I'm using. There's no extra condition created here. This is the general antiderivative. But that means all of the stuff we did where we figured out antiderivatives at the end of chapter 4 can now be written in these terms. All of these are known. I know how to evaluate all of these integrals, because evaluating an integral, in this case without numbers, means find the antiderivative. So what's the antiderivative of x squared?
1/3 x cubed.
But wait, that's important. I must have that plus c on the end here, because we are dealing with the general antiderivative rather than a specific one. The antiderivative of cosine of x. You all have a trig formula derivative sheet. You don't have to have this memorized. That's important. What's something whose derivative is cosine? What's something whose derivative is secant squared?
Secant x tangent x.
Go back and check our derivative formula sheet. It should be attached to your exam, or take a look on page 403 in our textbook. On page 403, we have a list of all of the derivative rules we had written backwards. Is he? Which one is it? I thought you were talking to me.
Oh, he said tangent.
Oh, good. There we go. Tangent of x. Nice cover. On page 403, I see this. This table, everything in this circle here is on the formula sheet we have, which means 1, 2, 3, 4, 5, 6. But let's take a look at these rules a little more closely. This first one says that if you take the antiderivative of something with a number in front, you just leave the number in front and take the antiderivative. This one says if you're taking the antiderivative of two things added, you take each one separately. The antiderivative of constant, that's a rectangle, so I get an x. But that's really the power rule, because I went from x to the 0 to x to the first. So here's the power rule. That's the one I actually need to remember. I have to have the power rule in my head. Power rule only works as long as my power is not -1. Because what's something whose derivative is next to the -1? Oh, right, that's 1 over x. And that antiderivative is the logarithm. Oh, and the antiderivative of e to the x is e to the x. Everything else in this section is on that formula sheet, except for these last two, because we didn't do those. That's chapter 6, chapter 3, section 11, hyperbolic functions. We didn't talk about those. Because they can be rewritten in terms of e, we'll just do them in e. It's easier, in my opinion. But that means just using those rules. 2 of these should be immediately obvious. We just said the antiderivative of 1 over x. But wait, there's more. Thank you. And the antiderivative of e to the x is e to the x. What about 1 over x squared? I'm sorry, 1 over 1 plus x squared.
Is minus 1 of x plus c.
That's our inverse tangent. Which, because it returns an angle, and an angle is an arc measurement, is also called the arctangent. Since we're going to see that notation as often as we see the tangent to the -1, I want you to have them both interchangeably. That leaves me with the square root of x as my only moment. When we did derivatives, how did we take the derivative of the square root of x? If I rewrite it as x to the 1/2, I can do the same thing for the antiderivative, because now that is a power rule. But notice I have not done the actual antiderivative yet. So the integral symbol and the dx are still there. It doesn't disappear until I do the antiderivative, which means I add 1 to the power, divide by that new power, and add c. But 1 over 3/2 is 2/3. If it says do not simplify, you can stop at the first one. But I think the second one's a little prettier. And if you're doing the flip the fraction out of the bottom in your head, you can go straight to the second one. But again, don't mess that up, and that's an easy mistake. I think it's worth writing down. But that one brings to mind the idea that I may need to do some work before I can do my antiderivative. So for example, let's suppose I see this one. Blah. There is more than one way to do this problem. But the other way to do this problem is a way I haven't taught you yet. So I go back to looking at page 403 at that table. And I think about all the trig function things I've got, and I go, wait a minute, there's some trig identities I can use here. So let's rewrite this. Cosine over sine is what other trig function?
Cotangent.
And cosine, because the cosine is on top. And 1 over sine, this is where I screwed up. 1 over sine cosecant. And now I look at page 403 at my table or at my formula sheet off the exam, and I say cotangent cosecant. That's on there somewhere, isn't it? Well, almost. Because what I see on the formula sheet is different by what? There's a minus sign there, right? It's minus cosecant cotangent. And that's the derivative of cosecant. But what do I do about the fact that I've got that extra minus sign? Well, that's where I can say that there's a rule at the very top that says if you're multiplying by a constant, you can put that constant inside or outside. So I'm going to cheat. And I'm going to multiply by 1. Like we did back in limits. Remember it then? And the 1 I'm going to use is a -1 times a -1. I'll put one of them on the inside and one of them on the outside. I'm allowed to multiply by 1 as long as I do it in a convenient fashion. As long as I obey the rules. But now the thing that's in there matches exactly the derivative of, what's the antiderivative of minus cosecant theta cotangent theta? Cosecant theta, Gesundheit. So except for dealing with the negative sign, the only thing that was involved here was turning this into something that looks like what's written on that formula sheet. This is going to come back to us on multiple occasions. I need to be able to use what's in front of me, the resources I have, and all the algebra and all the trig I've already learned to try and make my life easier. Let me change this problem just a smidge. Now, this may or may not work. I don't know. But what I do know is the way it's written is ugly. And if I try and split it apart, I'm going to get sine and then sine over cosine, which is tangent. Looking at our formulas, do we see anything with sines and tangents in it? Unfortunately, I don't. That's a problem. So I can't do that separation. That's a dead end. This is going to happen to me frequently. I'm going to say, well, let's try this algebra piece. And if it doesn't work, I'm going to back up and try again. So I back up and I say to myself, what else could I do? I go back to trig. and I say to myself, I have trig identities, don't I? About sine squared. My favorite trig identity in the entire universe comes to mind with sine squared.
The 1 minus cosine.
Pythagorean theorem, right? Sine squared plus cosine squared is 1. And if I do that, this integral becomes the integral of 1 minus cosine squared theta over cosine theta d theta. And again, I'm kind of happy about that because that's got a simple bottom, a simple denominator, so I can split it into two fractions this way. And I get the integral of 1 over cosine, and then I get cosine squared over cosine, which is just cosine. Oh, I know the antiderivative of cosine. That's on my sheet. What's 1 over cosine? Okay, so I say to myself, secant theta minus cosine theta. Do I know this one? Is there something on that formula sheet that's just secant alone? The derivative of tangent is secant squared. That's not secant alone. That's squared. The derivative of secant is secant tangent. That's not secant alone. None of my other trig formulas back there work for this. So again, I've reached another dead end. There's got to be a way to do this one. I just don't know how yet. Critical statement. There's got to be another algebra trick or another trigonometry trick that I don't know yet. And this is why antiderivatives are so much more difficult than derivatives. Because there are literally thousands of different things I could attempt to do. And that means I need to rig these problems to start with, to make them work out to stuff we've already got or stuff where I can manipulate like I did here. Now, maybe there's another manipulation I can do, but it isn't obvious to me what that manipulation is. So I'm going to have to put that off. And that's the answer at the moment. I don't know how to do this problem. We'll have to come back to it. So frequently, we find ourselves in a position where we are doing antiderivatives. And the algebra we are doing, or the trigonometry we are doing, the manipulation we are doing to the thing we are taking the antiderivative of, gets us stuck. If I absolutely 100% needed to know this antiderivative right now, I'd run over to a giant table. Because that table you have on page 403 has what? 18, 19 formulas, 20 formulas in it? I need you to look up for me on your device the CRC handbook for mathematics. CRC stands for Chemical Rubber Company. The CRC used to put out every year a handbook of chemistry and physics. And in the handbook of chemistry, which I kid you not, the first one I saw is 5 inches thick. Contains almost every fact you can imagine about chemistry. just about every known fact. And they update it every year. They put out a handbook of mathematical formula. They have an integral table in it, just like the one on page 403. It's got 1,100 integrals in it. There's a lot more going on here. Even our textbook provides us with lots and lots of integrals. This is in the gray reference section in the back of the textbook. Please notice, table of integrals goes up to 120. That's just what's in this book. And that's because the tricks we are going to learn over time are not new. They're just different manipulations to our integrand. Questions? Because more on that is coming. Another way to think of the fundamental theorem of calculus. We wrote that the definite integral from a to b of a function was you take the antiderivative, you plug in b, you plug in a, and you go off to the races. But we wrote capital F. But that's shorthand for exactly this indefinite integral that we've just been doing. So here's another way to write the fundamental theorem of calculus, and that means that every definite integral is really an indefinite integral first. Do the antiderivative, and then plug in your numbers. So if I want to do something like this, what I can do instead is say, hey, wait a minute, do this. Do the indefinite integral first. What's my antiderivative? Now, normally, I just did the antiderivative. I didn't talk about it. I said, well, we know how to take the antiderivative here. No, let's actually write that out. So first, I do this. We can write that word first. What's this antiderivative? The antiderivative 2x cubed.
1/2 x to the fourth.
Because it'll be 2 over 4x to the fourth. Same thing with the 6x. I get an x squared over 2. There's a 6 out front. 6 over 2 is 3. If I'm subtracting here, I'm subtracting here. 3 over x squared plus 1. I don't have a 3 over anything in my formula sheet. I have 1 over x squared plus 1. Actually, I think in the formula sheet, I wrote it 1 plus x squared. Big deal. You can add in either order. So that becomes 3. The antiderivative of 1 over x squared plus 1 is the inverse tangent of x. Now, since this is an indefinite integral, what has to be on the end of this? Without that constant, I haven't done an indefinite integral. Like I said to you, my high school calculus teacher, Maria Soto, took off a point every time I forgot that plus c. I got negative scores on a homework assignment because of it. But now that I know that, I can do the definite integral. And I can say the integral from 0 to 2 of that same function is this antiderivative evaluated at 2 and at 0. And at that point, I can drop the plus c, because the fundamental theorem of calculus allows me to use any antiderivative, so I might as well use the one where c is 0. Unfortunately for me, the inverse tangent of 2 is not a number I know. I go to plug in 2, and I get 1/2 2 to the 4th minus 3 times 2 squared plus 3 tangent inverse of 2. And then I go to plug in 0. And tangent inverse of 2 is not one of my reference angles, because when I go back and I think about the angles in the first quadrant, I have 0 and 90 and 30 and 45 and 60 all in degrees. Their tangents are 0, undefined, 1 over the square root of 3, 1, and the square root of 3. 2 is not in there. So if I want a number for this, I'm going to have to go to my calculator. 1/2 of 16 is 8. 3 times 4 is 12. Plus 3 times, somebody give me a number, at least 2 or 3 decimal places, for the inverse tangent of 2. Yeah?
1.1071.
There we go, 1.107. 0 to the 4th is 0. 0 squared is 0. The inverse tangent is 0. Is 0. So everything in that last set of parentheses turned out to be 0 this time. So I get a negative number for an answer. The more decimal places you use in your inverse tangent, the more decimal places you'll have for an answer. How many decimal places are appropriate? That's where the sig fig argument comes into play, and I'm not a science person. Questions? The integral of the quantity y plus 5y to the 7th over y cubed dy. Remember, the letter itself in my antiderivative, in my integral, is completely irrelevant. I can use any possible letter you want. Y, T, X, Z, theta, alpha, I don't care. You can use whatever letter is appropriate to the problem. This problem, I happen to do the integral in y. Whee! But I go back and I start looking at my formula sheet and I say, I don't know how to do the quotient rule backwards yet. Nothing that we have done has prepared me to do the quotient rule backwards. Now, for the record, the conference I was at 2 weeks ago, a young man from the University of Pittsburgh actually presented a paper asking why there isn't a method that is well publicized to do the quotient rule backwards. An undergraduate math major at the University of Pittsburgh gave a 15-minute talk on why there is no inverse quotient rule yet. And the answer is because it's ugly. It works, it's just ugly. So there will be a way to do the quotient rule backwards. It's just not fun. So we're not going to get there yet. So how can I do this avoiding the quotient rule? Leo?
So could you divide like the y by y cubed and plus 5y7 by y cubed.
Exactly as we did with the sine squared over the cosine, I can break it up because the denominator is simple. And that means that this is really the integral of y over y cubed plus 5y to the 7th over y cubed, which is much easier, y to the minus 2 plus 5y to the 4th. And that's power rule. So again, just as I did above, I will say that the first thing we need to do is an indefinite integral. Find me the antiderivatives. But that's an extra step. You don't have to do this separately. I just chose to. If this power is -2, when I do the antiderivative, the power is bing, the most common mistake made in doing the power rule. I'm adding 1. -2 plus 1 is less negative.
That's negative.
Exactly. Thank you. I have to have somebody do it every semester, and it's usually somebody in the room. So thank you. So I get y to the minus 1 divided by minus 1. And then this one, y to the 4th, becomes y to the 5th. It'll be divided by 5, but there's already a 5 out front. How convenient is that? And I have to put the plus c on this because it's an indefinite integral. And that means that now I can do this. And that's negative y to the negative 1 plus y to the 5th. And now I can turn the c into a 0 because I'm doing a definite integral. I can use any constant I want. But now I evaluate. So I get parentheses -2 raised to the negative first power plus 2 to the 5th minus -1 raised to the negative 1 power plus 1 to the 5th. 2 to the negative 1 is a half. So this is -1/2 plus 2 to the 5th. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 again is 32. Minus 1 to the negative 1, that'd be 1 over 1 with a minus in front of it. And then 1 to the 5th power is 1. Wait a minute, -1 plus 1. That cancels. How convenient. So I get 32 minus a half, or 31.5. Questions? An integral, a definite integral, we interpreted that as the area under a curve. You had a problem in the homework I just gave back about finding the distance traveled by a car as it was accelerating, right? We had speed in kilometers an hour, and then we had time, and we had to count areas. But that meant that when I did the definite integral, my answer was distance. So that's what the fundamental theorem of calculus tells me. The integral from a to b of little f of x dx is capital F of b minus capital F of a, where capital F is an antiderivative of little f, or where capital F's derivative is f. The derivative of distance is velocity. So when I integrate velocity, I get change in distance. Okay. I'm going to throw an object straight up into the air. Or I'm going to let it go from a particular height. Take your pick. We have all sorts of options, right? Actually, run with this. I have an object here. What's this antiderivative? What's this definite integral? Give me a number. What's going on here?
That's when I use velocity, because it's v of t.
I'm perfectly fine with that. But what is my actual change in distance? Work it out. Do the definite integral. Take an antiderivative, plug in the numbers, tell me what's going on. What's my antiderivative?
T squared plus 64t.
Okay. When I put in 4, 16. When I put in 0, 0, 0. Zero squared is 0 times 0, 0, that's 0. 4 squared is 16. 16 times 16 is 256. Four. Wait here. I have a velocity. My velocity at time 0. Velocity at time 0. At time 0, I am. How is it I went? My distance. Change in distance. I go. No, I started at home plate. I ended at home plate. If I go where I have to do, I have to touch all of those other places. Because if I didn't go, this is not change in distance. This is change. Displacement. Am point to ending point, not how far I went in between. There is 64. But I also spent time down. And as a matter of fact, this object starts at 0 and ends at 0, reaches its highest point at exactly 2. So we spent 2 seconds going up, 2 seconds coming down, and ended it by net change. And that's an important point, because what that is that this here that's net change. Change in distance, net change in distance. If the distance traveled, then back up was counted. So I make a minus sign for my velocity. Total. Then I need to do the of my velocity. Because that's backwards and the distance I travel forwards. I'm not going to have any area under x-axis. This is negative. I need to count those distances as positive things. It would do to me. But now I know where this function is sign, where velocity is being positive and negative, and look at v of t. I see its graph as a string. And the, well, t-intercept is. So I would really two to do the integral, the absolute value I would have to do the integral from 2 and then a different integral from 2 to 4. The problem along the way from A to B, I could go from A to C. Here I change. When I do the absolute numbers need to be here. The function is negative 32 plus 4. But here, the function is the opposite. That extra mind because I have to move here. Now that actually just means that I can write this as the integral from 2 to 4 of 30t minus t4. Problems are both easy to do. Please note that your net distance turns out to be 128 feet, 64 going up and then 6 coming back down. Make sure that's what you get. This of net applies to any station. Let's suppose that the volume of water into or coming out, that rate of change is of something. If we're going in or out, feet per gallons per day, something like that, right? But if my volume of water changes over time, then I integrate t prime of t. But when I get back the original function, and b minus v of a, that represents the total water out, the change over the course of that. Now that means in the morning, it gets up and showers, makes coffee and cooks breakfast, the dishes, goes down. The water back up. All I know is the difference between time A and the difference between time B. Is there more water or less water than there was earlier this morning? Function. So that's the cost unit at a production level of X. Well, then because market is derivative of cost. You want to increase how many units you're making, how many a year? You want to level from A to B. You at the total in cost. Measuring, and this gas is heavier than air. That means it move uniformly across the tube, right? But concentrated, it will be unless that total weight, because density gas per cubic centimeter. Great. If you're measuring how things change and you want to total that up, that's an integral. Single field of study. I don't care what you're thinking about. I don't care what field of study it is. There's an integral in there somewhere. Next on the agenda is ways to do more rules, because I have so many dead ends. I want to be able to do more of these tricks. It turns out the next easiest rule to work in is the chain rule. Surprise, that's actually easiest. That's what we'll start with tomorrow. I hope you have a wonderful day. I'll see you then.